this position and momentum are continuous, and because of some rules about group theory, that basically restricts me to having both of those be real numbers. And these can be mechanical or electromagnetic, and there's roughly big sort of 4 physical settings relevant to that. One is the one I grew up with, which is just boxes of metal, empty boxes of metal, where you can have like these, solve Laplace's equation, and in each you get a bunch of frequencies that fit in this box, and for each frequency you have a wave, standing wave in there, and if you cool the box and make the wave sufficiently small, then the amplitude of the wave starts to be discretized in terms of photons, right? And that's the type of setting that this type of bosonic codes very much apply. This is one of the dominant technologies right now, where things have been realized that you may have not thought could have been realized. Motional degrees of trapped ions is the other one, so this is literally the ion moving in a trap, represents an oscillator. The other one is some more up-and-coming technology, but also very much oscillator dependent, so vibrating small pieces of metal, drums and things like that, nanoacoustics, mechanical resonators, and of course, the workhorse of almost all communication, optical fibers, and in general, actually, more generally, free space transmission of electromagnetic waves. And it's nice when you work on bosonic coding, you kind of can cover all of this in one formalism. I mean, the noise models are slightly different, but some of the noise models are actually the same for these things. So these all suffer from noise, as you know, and you need to encode things redundantly in these systems in order to preserve quantum information in, say, a memory, or try to transmit quantum information over, say, a link. And these systems, because of the infinite dimensional nature of because of their infinite dimensional nature, they are large enough to already be useful for redundant encoding. You don't need to scale these systems up in order to have a code. You can already fit enough things, you can already do some redundancy within the system. And that's what bosonic coding is in some sense about. This is more for the experts or for those already familiar with a lot of this. I'll just flash some buzzwords here. So you can think of a qubit as a particle on a pizza, and an oscillator would be taking the pizza, making the slices infinitely thin, and popping it open and making it a line. And the canonical basis states of an oscillator are just these of a qubit are these bit string states that we discussed last time. For an oscillator, the main state that I'll be using to define codes today, or right now, is this position eigenstate. And x here is a real number. I'm going to go into these a bit more in a bit. But I just want to, again, flash some sort of rough equivalences. There's a set of easy states in the discrete variable land, and there's analogous sort of easy states and continuous variables. We'll go to analogs of the Paulis, which will be displacements in the position and the momentum of the harmonic oscillator. There's analogously easy sort of operations and channels, and these are also called Gaussian operations and Gaussian channels. And with qubits, you can do Pauli measurements and get all these expectation values and plot the state. And similarly, there's very physically relevant ways to do that in an analogous way for the oscillator, and including this Wigner function here, which is plotting expectation value of a certain operator that's parameterized by a complex number. So it plots it in the complex plane, where the real part corresponds to position and the imaginary part corresponds to momentum. Okay, but for the computer scientists out there, I did want to get into this a little bit more precisely, because naturally computer scientists don't like infinities. So please don't be scared of infinities. These are pretty harmless infinities, trust me. I would be scared if they weren't. So we're going to be dealing with, in the following 2 lectures, with basically 2 different bases. You've already seen the Fock basis, which is this one over there, but today I'm going to focus on that quote-unquote basis and expand and express code states in that basis. This is called the position state basis. Why am I using basis in quotes? Anybody know? Because it's not really a basis, right? But it is analogous to the qubit case. It's actually, to me, more analogous to qubit basis than it is than the Fock state basis is. So these states, I'm going to stop using air quotes, just use them for me in your head, are not normalizable. So they are orthogonal, but their normalization is infinity. This is the Dirac delta function, which is infinity if x equals y and 0 otherwise. So this seems like a problem, but it's actually not something we can, it's not something you have to worry about too much. Moreover, even though these things are not proper quantum mechanical states, you can never focus your oscillator or put it in a specific position because that's requiring infinite precision, that requires infinite energy, and your state, it just can never be like this. You can make such position states to good approximation that are also normalizable. So whenever I work with these are idealizations. You can maybe think of them as integrals, but when you work in the lab or when you work numerically, of course, you're going to be dealing with sums, right? So again, computer scientists, don't run away. And what's beautiful about these is actually they, even though they're not orthonormal, they are complete, meaning that you can use them to resolve the identity. Moreover, operationally, physically, you can actually measure in these things. So even though they're not a state, you can still measure in them. It's kind of maybe strange if you think about it a little bit, because you're measuring them. Do you really collapse to them? If they're not states, right? But nevertheless, there's a mathematical formalism of that's sort of extending projection-valued measures to these types of non-normalizable projections, which is perfectly valid, and moreover, it corresponds to homodyne detection, which is extremely ubiquitous in photonic systems. Who's heard of homodyne detection? Who's actually heard of it and remembers the formula for it? It's a scary-looking formula. Yeah, okay, I've heard about it for 10 years, and the first time I saw the formula was like last year, and it scared the crap out of me. It's actually, but anyway, I have it in it. No, I'm not going to show it. I don't want to scare people. It's in a different talk. Just wanted to show you that the math here is actually quite subtle, that it's possible to measure in such a basis. And this isn't the only basis that you can do this with. So these types of distributions, they're not really states, they're called distributions, you can measure in distribution valued measures. So, but quantum states, so what are quantum states? So there's such a thing called an occupation number here that measures, so I'm going to expand this one in the Fock basis, that just is a diagonal operator in the Fock basis that labels how many photons or phonons or carriers you have. And this thing is a rough sort of metric for the energy inside your system. And I'm going to claim that quantum states are all those that have finite powers, finite expectation values of all powers of this thing are finite. So the first power of this, the 0th power of this thing is normalization. The first one is the energy. The second one basically is the variance. The third one, etc. And usually people just assume that, and people in qubit land assume that any state that's normalized to 1 is a valid quantum mechanical state. However, in these spaces, you technically also should require that not only is it normalizable, namely the L equals 0 moment is finite, but also that it's finite energy, it's finite variance, finite cubic moment, etc. So mathematically, for all of these even for these types of homodyne measurements to go through, this has to be the case. And so mathematically, if you want to be rigorous, it's assumed, sometimes implicitly in the physics literature. Physically, it's also implicitly assumed because I have yet to see a state that doesn't satisfy this. So both on the math side and on the physics side, it seems to be happening, but nobody really define states this way, but anyway, so I'm going to do that. I'm going to say the states are not actually all the states that are normalizable. It's only those states that have finite moments for all possible moments of the energy. And those states form what's called Schwartz space, not Hilbert space. So anyway, it's just some subtle thing that's actually kind of physically relevant. Who's heard of Schwartz space?
No, it's nothing to do with Schwartz. It's Bosonic Coding. It's not complete.
And yeah, so this is a subtlety that I don't know much about, but it's also something that you don't need to care about in finite dimensions. So see, one of the first slides, you already see some intricacies of infinite dimensions. Okay, so I'm going to describe for you to this lecture, I'm going to describe to you this class of codes called bosonic stabilizer codes. And there's different types of bosonic stabilizer codes, and they're quite different, but they are based on a pretty robust extension of the stabilizer formalism that you saw in the previous lecture, 2 bosonic modes. Basically think stabilizer formalism, but with many more continuous things. And the next lecture, I'm going to describe to you states that are more easily expressible in this Fock state basis, which I call Fock state codes. And those will not correspond to a stabilizer formalism, or they will not have a very good stabilizer formalism associated with it. A lot of the features of the formalism will be lost. And so those types of codes have to be interpreted in a different way. But the first codes for this lecture are going to be very much nice extensions of the stabilizer formalism. And you can roughly see that there's this sort of a translation type flavor going on for these types of codes. And there's a rotational sort of degrees of freedom and rotational noise that these codes are protecting against. Okay. So that's for this lecture. So, all right, so let's see. The noise model we're thinking of, as I said before, is a sort of a translation-based noise model. And we're going to define position shifts, so things that change the position of the oscillator by, say, this amount Q. And they act on our position states. So position states will be the state I'm using throughout the whole lecture. And they just shift the position by Q. And then on the other end, we're going to define momentum shifts, which are sort of the sigma z counterpart to these position shifts. So if these you can think of as analogs of sigma x, these you could think of as analogs of sigma z. They are diagonal in the position basis, and they just spit out a phase that that sort of marks where you are in the position space. And these are written in terms of these position and momentum operators, which have a commutator that commutes to I. So how much of this have you sort of familiarized yourself with before? Maybe amongst the computer scientists, are you okay with the X's and the P's, or do you want me to go? Feel free to let me know if you want me to go. Yeah.
So your exception to the first line, first derivation in your plot. On the left-hand side, you have an extension from the position eigenspace that seems to be uncountably infinite.
Yep.
On the right-hand side, extension to number eigenspace which seems to be uncountably infinite.
Correct.
How can that be the same? How?
Because the position eigenstates are not a basis. They're these fake states that you can use to describe things in an uncountably infinite Hilbert space. So the real basis is this one. And this always exists for any Hilbert space that is countably infinite. And these are just another way to understand that countably infinite space. Now, there's a separate Hilbert space. Sorry, I don't even know if it's a Hilbert. Maybe the mathematicians can tell me. But there's a separate space which does have a basis which is uncountably infinite. That space happens when you take the number, when you have n qubits and you take n to infinity. Now there, you have the basis of all infinite bit strings, which by Cantor's argument actually is uncountable. Because you write them down, all the bit strings, and then you pick a diagonal, and then you flip all of them, and that one is not in your list. Remember this argument? So the thermodynamic limit of n qubits is indeed a space with an uncountable basis. And that's a whole nother monster that people spend their lives studying, right? All sorts of interesting stuff happens in the thermal limit. This is not that. These position states are a fake basis. They're not really a basis. They're just a way to conceptually understand and write sort of extreme points in this space that don't really exist, can be used for measurement nevertheless, and correspond to idealizations of physical states, which are highly squeezed states in position or in momentum or in any other quadrature. The sigma x and sigma z are what? Heisenberg-Weil operators, yes. Yes.
So this is the analog of qubits, not of n.
This is the analog for a qubit, yes.
So what is the analog of an n qubit?
Well, n of these. So then you have n modes. You have q1 through qn, p1 through pn, x1 through xn, and then you have tensor products of these Weil operators on each mode.
Yeah, but you said that the signal to n qubits when you take n to infinity.
No, I said that's not, not similar. No, n qubits with n to infinity is a whole different beast. Think type 2, 1 factors and all sorts of crazy stuff. This is very much simpler. That's uncountable, this is countably infinite. Okay, so we have our error operators, and general errors, just like in the Paulis, can be written as as linear combinations of products of these types of momentum and position shifts. So think of this as your analog of the Pauli basis for a harmonic oscillator. So now we can think of sort of simple codes already. Remember our repetition code when we had 0 go to 0, 0, 0, and 1 go to 1, 1, 1? Well, we can do a bosonic analog of that by just having x logical go to x, x, x. And this type of very naive extension gives us actually codes that are fairly relevant. Now, one important thing about these types of codes, which I'll be calling analog stabilizer codes, they're often called linear oscillator codes, Gaussian oscillator codes, etc. They do not encode a finite dimensional space in the space of the modes. They encode logical modes into physical modes, just like the qubit codes encode logical qubits into physical qubits. So it's infinite to infinite, modeling the finite to finite encodings of qubits. And this is a classical version of this. This is a classical code. It's an analog of the repetition code. And it protects against shifts of one of the three modes, right? You can still use majority vote, you just have a continuous coin, basically, is the idea, okay? Now, and you can go quantum with this as well. You can cook up an analog for mode code, which is an analog UE of the 4-qubit code. And this encodes one logical mode into 4 physical modes and protects against any single mode error. So if you remember our form of the 4-qubit code, we actually had written it out in a better way. We had it like this. All right, proportional, 2 Bell states tensored twice, and you can do a similar thing here. So here, I forgot to mention that there's a dual state to the position state, which is a momentum state, which is just equal superposition of all position eigenstates with some phase weighting factor. And this is your analog of the plus-minus basis for a single qubit, not to be confused with the plus-minus I had used in that slide. And this is Fourier transform away from the position, right? So these types of states protect, if you do a repetition code of these states, they'll protect against shifts in the momentum, not in the position. And if you concatenate the momentum, the position, the momentum repetition codes, you get precisely this 4-mode code that I wrote down. And it's, again, sort of this 2-copy generalization of a Bell state, and then tensored twice. So more generally, so let's look at this 4-mode code in more detail. It also has some stabilizers, just like the 4-qubit code did. And in this case, the stabilizer group is a continuous group. Roughly the only difference is that the domain here of the powers that you're allowed to take of this group is not, Z2 is not either 0 or 1, but it's all the reals. And so that's what I mean by continuous group. And the 3 operators here, S1, S2, S3, are basically your analogs of your ZZ, II, ZZ, and XXXX. There's some minuses here because if you look at the qubit version of these codes, this is actually ZZ dagger, and XXX dagger, X dagger. So these are very natural versions of these qubit stabilizers. Now, because the stabilizer group is continuous, we can do something here that we will not be able to do with the rest of the stabilizer codes. Namely, we can look at the group's Lie algebra. Remember angular momentum, SO3, SU2, Lie algebra, LXL, YLZ? Well, you got the same thing going on here, except here the Lie algebra is much simpler because these things wind up actually commuting. The things upstairs will wind up commuting with each other. And the elements of the Lie algebra of this type of analog stabilizer code group are called often nullifiers or annihilators. And because the code states are +1 eigenstates of the stabilizers for any alpha, for any A, it has to be the case that the annihilators literally kill the code words. So they annihilate the code words. So we can see, for example, here, we'll go through this first guy. If we apply X2 to X4 mode, this is hats, and move it through the integral. So these X1 and X2 only act on the first 2 modes, so we can kind of shove away the last 2 modes to the side here. And then so X1 hat, just like the occupation number, is an operator that spits out the label of the position state you're in if it acts on a position state. So it will spit out the first Y, this one, and then X2 will likewise spit out the second one. And so you should see that this is identically 0. Yeah?
With the analog, what you see, it's really, is it the 0 logical or the 1 logical? Which one we're looking at?
Exactly. So X here is an index for the logical position state, which is any real number. So instead of 2 logical states, now you have a continuum of logical position states. I'm giving you a basis for a countable Hilbert space, countable logical Hilbert space, using these position states. I can likewise define other bases for this countable Hilbert space of the logical mode, but these are the easiest ones, as you probably see, to define because of the direct correspondence to the qubit case. So these analog stabilizer codes, everywhere you see a binary number, you stick in a real number, and roughly that you get these codes. So the logical mode has a continuum of basis states. So So this is X logical. So these are the code words. The code words are now code words of a logical mode, so they are indexed by a continuous degree of freedom, namely the position of the logical mode. Just like code words here of a logical qubit were indexed by 0 and 1. So these analog stabilizer codes, like I said, they're very easy to construct from qubit codes, but they encode a logical mode or modes, k logical modes and n physical modes, and they also protect against noise, arbitrary large shifts acting on at most d minus 1 of the modes. So the notion of distance here for these codes, for these NKDR codes, is sort of the same as in the qubit case, but now looking at oscillators, it's protecting against arbitrary errors acting on only some subset of the modes. Yes?
Maybe for clarification, so like time multiplied by an element which is non-negative, I guess, new element with eigenvalue 0 still, right? So, is that a problem?
In what sense? These are an algebra. This thing? You don't like, why is it not a group? I mean, it's, you can revert, you have inverse.
The eigenvalue 0 and the, like the leading, the algebra element is 0 and then you have the eigenvalue 1.
Yeah, you're exponentiating these. So e to the I 0 is 1. And that has to be the case. So like this is if and only if. Yeah. Yep. Right. Well, you substitute squeeze states for these position eigenstates. So these are idealizations because they're useful for the code construction to be simple, but in reality, there's a process of using normalized approximate versions of these states where you have to take care of two infinities. One is the infinity arising from using this non-normalizable state, which you can approximate with a highly squeezed state. And two is if you have an infinite number of these, so the integral here, you might have to dampen the, you do a regularization inside here, like a Gaussian as a function of z in the integral. Yeah. So in my notes, there's a sort of a section about that, but I didn't want to get into that too much, but you're right. These are like, think of them as integrals. In reality, you're using sums. Okay? In reality, things are normalizable, highly squeezed.
In order to talk about a new algebra of the group, something needs the exponent to be continuous, so like if you find an alpha, it can be as small as we like, and like it's the exponent to the alpha parameter and to talk about
I mean, I get these by taking A, B, C here to be arbitrary small, Taylor expanding. No. See, that's why I'm saying here. It's a continuous, yeah. And this is the first and last time you're going to see such a group for the stabilizers, okay? These are relevant to, well, they sort of used to be the prime analogs of cluster states for continuous variables. You can kind of maybe see how you can define cluster states using these states. In fact, cluster states are analog stabilizer code words, okay? Just like qubit cluster states are stabilizer code words. Here you have an analogous construction for CV cluster states, storing. What? Oh, okay. But maybe I thought you were saying that there's been some more developments in cluster state literature where they are working on storing finite dimensions, and then you have to use these codes that I'm about to introduce to you. But in the original formulation, if you want to store infinite dimensional logical information, these are precisely the types of states you're using. Okay. So we saw that we can cook up stabilizer codes using a group of displacement operators, right? So this stabilizer group, it's the joint plus one eigenspace of all of its operators is indeed the code space. So it's, again, the same definition of stabilizer as before. And it consists of a continuum of different displacements. So you see the displacements are starting to play the same role as the Pauli operators did for qubits. And the role continues here because there's many different types of groups that you can construct out of these displacements. And so we're going to construct a different group that's not going to be continuous, it's going to be discrete. So the displacements don't commute with each other, and the formula for not commuting is as follows. It's this sort of the group version of this commutator. So you move this through the other. That's a Q2, e to the minus I Q1p. And then this is the commutator, so it's this Q1, Q2. Okay? So to construct a stabilizer group, we just need to pick a commuting set of displacements. Before, we had picked superpositions of positions and momenta that themselves commuted, so everything was fine. So we could raise them to any power, and we got this nice continuous group. But now I can show you that we can pick another discrete group of commuting displacements that we can already do in one mode only. We don't need multiple modes. And this yields the GKP codes, or Gottesman, Kitaev, and Preskill, which are based on the same displacement stabilizer group, but now the group is discrete. These codes, besides the group, them being constructed from a discrete group, they also have two other features that are notable here. They have a finite dimensional logical subspace as opposed to an infinite dimensional one. And their notion of distance is different. They protect against sufficiently small displacements on all modes, as opposed to the previous analog stabilizer codes protecting against arbitrarily large displacements, but only on a subset of modes. Okay? So they're very different beasts, but but they can be also handled with the stabilizer formalism. So let me just introduce you this stabilizer group. This group is now, okay, discrete. I'm only allowing for integer powers. And now my Q1 here is square root of 2 pi n. My Q2 is square root of 2 pi n. So what's e to the I Q1 Q2? E to the I 2 pi n. And that's otherwise known as 1. So these displacements commute. And they happen to be both within one mode. So already within one mode, you can construct this logical space. And I have to show to you that, well, you may have to take my word for it, that they do house a qubit's worth or a qnit's worth of logical dimension. So their joint plus one eigenspace is a qnit for n. And for n equal to 2 here, which we're going to handle, the logical basis states are expressed as follows. And here we can show why this is the case. So it's easy to see that these are plus one eigenstates of both S1 and S2. So if you have S1 act on a position state which is an integer multiple of square root of pi, this state is all the even multiples of square root of pi, and this one is all the odd multiples of square root of pi. So basically, we just have to make sure that if we make sure that this is a plus one eigenstate, plus one eigenvalue eigenstate, then all of those other ones are. And it is, if we just plug this in. I never get the 2's right. So that's from the square root of 2 pi n, and then x hat becomes L square root of pi. So this is, yeah, square root of 4 is just 2. Pi L. So this is a plus one eigenstate. So the position state that you pick is a comb or 1D lattice of position states such that each position state is an eigenstate of this momentum shift operator that's an exponential of the position. So then we're good here. These states are indeed plus one eigenstates of this first generator. What about this one? Well, this one generates shifts in position by how much? By square root of 4 pi, otherwise known as 2 square root of pi. Well, these are all even multiples of square root of pi. So if you shift them by 2, does it change? The comb is left invariant. The 1D lattice is left invariant. These are all odd multiples of square root of pi, also don't change by shifts by 2 times square root of pi. So this momentum shift is also leaving the codes invariant, and so these are eigenstates with eigenvalue plus 1. So this is so this is indeed the stabilizer group of this code. Now, what does this do? So I mentioned that this protects against sufficiently small shifts, and it's very easy to see that by just looking at the structure of these cones. Let's consider some shift, okay? It's going to just move all these cones like this. Let's say a position shift. And now as long as this shift is detectable, as long as you leave the code space, right? So you detect shifts up all the way up until you go hit back the original, one of the positions of the lattices here. There's a logical 1 lattice and a logical 0 lattice. If your shift is sufficiently large, then you have a logical X error happen when the black dots and the white dots exchange positions. That's no longer a detectable error. But otherwise, the errors are detectable. And the yellow region here, without including the white points, demonstrates the detectable region of the code. Okay? Now, what about correctable regions? Okay. So correctable region is roughly half that, because once you shift past this in-between point, then your recovery operation will map you to the white points, and if you were a black point that's in this unit cell of the white point, then you'll be mapped to a white point, and your lattices will change places, and there'll be a logical error. And so correctable shifts are only shifts in the green region, which is this smaller region around 0. So this is the unit cell of the combined lattice, right, of both cones, while the detectable shifts is the unit cell of one of the lattices, okay? So, right. And how do we detect these shifts? What is the actual cycle of error correction that we have to do to correct, to stabilize these code words? What do we measure? Yeah. The generators. The generators commute, right? Let's measure them. Their eigenvalues are no longer plus and minus 1. Their eigenvalues are, because they're non-compact U1 generators, their eigenvalues are phases. So they have this continuum of phases. And for each value of the phase corresponds to an error space. And these error spaces, they wind around. So each of these shifted lattices corresponds to an error word. And each one is labeled by one of the phases. And the phases start to repeat. So eventually, you'll get the same phase labeling a different error space. And so you can't correct shifts that are that far. You can only correct ones that are closer. So you have to measure these two phases. And these two phases correspond to extracting information about the position and the momentum of the mode. However, you don't extract the precise position or momentum of the mode. You extract only the position or momentum of the mode modulo the lattice spacing, also known as the modular position and the modular momentum. Okay? And this is sort of the theme here for continuous variable codes. Remember, you need quantum numbers that are not too good. And if you measure position using homodyne or something, it's going to be too good. It's going to collapse this whole lattice to just one point. And so you want to extract something that gives you just enough information to resolve the error states, which in this case is the modular position and modular momentum. And even though, I just want to harp this a bit more, even though regular position and regular momentum do not commute, modular position and modular momentum do commute, which I think is quite, if you haven't seen this before, it should be quite interesting to you. You should think about it. Yeah? The generators are unitary, yes. I mean, yeah, phase estimation, do the plus minus Hermitian, anti-Hermitian combinations of them, you know.
You do the combination, and aren't you getting too much information?
cosine and sine. Should give you the phase. Yeah, well, on that note, actually, let me tell you something. So theorists come up with these codes, Goddess, McTav, and Preskill. People, first of all, think this is nuts. This can't be ever made. What is this? This is crazy. And second of all, like, the syndrome here is continuous, okay, right? Because this is a continuous variable code. And so experimentalists have to extract the syndrome. And to measure a syndrome that's continuous, you need to have an ancilla with continuously many outcomes. You no longer can do with binary ancillas. You don't just have plus or minus 1. You have many of these. Let's say you discretize them. You still need an ancilla with more than 2 outcomes, you would think. And then the experimentalists cook up a way to extract just the first bit of this modular position and modular momentum. They did this at Yale a few years back. And it works. So the theorists say, okay, no, you really need to use a continuous ancilla for this code because there's many syndromes and there's many shifts. And the experimentalists are like, we don't care. We're just going to measure the sign. And then they're able to stabilize these code words by just measuring the sign of these things sufficiently fast enough. I think this is quite conceptually interesting because this provides recipes for realizing error correction cycles of codes that at first seem like they would require a lot of overhead in terms of ancillas, but actually do not if you're clever enough about how to choose your ancillas and choose what to measure. So it's kind of like shifting the mindset here with theorists.
Can you explain again how you can avoid making these how continuous measurement and measure only the first bit and get away with it?
Well, not really. I can't because it's hard for me to believe myself, but the experiments say that they did it. I would say that I would only add that if you think that the displacement is sufficiently small and then sort of knowing the sign of it is already enough to figure out, okay, knowing the sign of it is already enough to figure out which way you shift. And then if the amount you shift is somehow always around the same amount as the amount that the error of the error, then you could imagine always kind of going back to where you started. And in the experiments, the protocols basically do that. So the best explanation I found is in this PRL in the appendix of Baptiste, Gervin, and one other person, Schrader, I think, where the type of recovery that they apply is basically a trotterized version of the actual recovery that they're supposed to apply. So there's a C0 type gate, as usual as it is with these cases, but it's like a trotterized version of it. And to the first order, this actually does work out. And then that's apparently, the lab has calibrated, in the lab, the things are calibrated such that this actually works out. Now, what I mean by works out, the first paper that did this experiment broke even, meaning that it was able to perform error correction cycles that gave a decay rate, a logical error rate that was about the same as if you had not encoded the information. That's called break-even error correction. The next paper realized like a few months ago went beyond break-even, but there they used a reinforcement learner to cook up some exotic recovery that was super tailored to the specific system using AI, in which they were able to have a logical decay rate, a logical error rate that was less than the physical error rate. But they were only able to do that not using conventional GKP type recovery or any trotterization of that, but some machine learning thing that you need more information to understand. I should really link these papers, but yeah. All right, and then last one is GKP stabilizer codes. This is a third type of stabilizer code, yeah.
This is something stupid, but I'm not sure what that is for. Can I just multiply everything by 2 and then get like 5 more distance?
Good. So no. But why? Right. These codes are based off of a square lattice in phase space. So I showed you how they protect against shifts in position. But because these are equal superpositions of position, if you look at the Fourier transform of these, you get equal superpositions of momentum, and the same comb picture applies for shifts in momentum. And if you plot these in the full phase space, in the position momentum phase space, you get basically a square lattice, okay? And the generators of the lattice are precisely the stabilizers, okay? And they generate a square lattice because you see the shifts here are the same. You can make the lattice rectangular by making one of the displacements larger, the other one smaller, and that code will protect more against one type of shift than the other. But because you made the other one larger, you have to make this one smaller to compensate and to make sure things commute. Okay. Similar things, it's a trade-off. Similar trade-offs happen in all error correction, in all quantum error correction. So you can protect against more, remember the M1, M2 code, quantum parity code that I had? You had M1 and M2 for the phase flip and the bit flip repetition. If you crank up one of them, you're going to have really good dx, x-type distance, but really bad z-type distance. And your actual distance is the minimum of the two, vice versa. So these trade-offs happen. The more phase flips, the less bit flips, and vice versa. And here it's very much nicely presented by the lattice. Now, these codes can be defined for multi-dimensional, for multi-mode systems. And in multiple modes, you need, in n modes, you need 2n stabilizer generators. Just like in one mode, you have 2 stabilizer generators. And those stabilizer generators can be defined using a matrix that defines the basis vectors of a lattice. That lattice needs to be symplectic because the stabilizers need to commute, and the commutation requirement is equivalent to the lattice being a symplectic lattice. And so now you can imagine if you've read SPLAG, who knows what SPLAG is? Conway-Sloan, sphere packings, lattices, and groups. You can imagine going nuts with all these different exotic lattices, and this is something that people are actively doing now. There's connections to lattice-based cryptography that are being very much in the infancy of being developed here, and there's lots more work to do here. Good lattices give you good gates, etc. Okay, so just one real quick thing here. I told you that an n-mode GKP code can be defined using 2n stabilizer generators that give you a lattice that fits into the 2n dimensional phase space of the n modes, just like here I've shown for n equals 1. This GKP code encodes a finite dimensional code space whose dimension is equal to the determinant of the lattice matrix. Now let's consider taking 2 stabilizers out of that stabilizer group, 2 stabilizer generators out. Now we have n modes, but we have 2 times n minus 1, 2n minus 2 generators. Now we have a discrete stabilizer group, but because we've removed 2 stabilizers, we actually have an infinite dimensional logical space. So we have a GKP type code that encodes infinite dimensions using a discrete stabilizer group. This is called a GKP stabilizer code. Now what does this code do? Well, besides encoding an infinite number degrees of freedom, it also winds up protecting this infinite dimensional logical space against sufficiently small single mode displacements. Now this is quite remarkable when this was first discovered by Kyung-Joo No, Steve Gervin, Liang Jiang, maybe 3, 4, 5 years ago, because nobody had thought that you could protect an infinite dimensions worth of information against small displacements. But these types of codes, in fact, do that. And the reason they do that is they basically use these GKP resource states and read off as ancillas. And after noise hits you, they use these GKP, so they're able to measure and extract 2 syndromes per rail, the modular position and the modular momentum, per mode. So they get, 2 n minus k syndromes here, and so they gain partial knowledge about both the position shifts and the momentum shifts that happen in the logical modes. And this gives you just enough information to be able to, in some cases, suppress the logical noise of these infinite dimensional logical systems. And you can think of this as a resource state here that's being plugged into these ancillas. That's, whoever knows what Gaussian is, this is a non-Gaussian resource in this context. Because if you plug in a Gaussian state here, something like a 0 position eigenstate, then you're back to analog stabilizer codes, which again encode k modes into n modes. But those codes do not protect against sufficiently small displacements on all modes. They protect against arbitrarily large displacements only on a fraction of the modes. But if you substitute back GKP, there exists a way to decode such that you can correct, or you can protect against sufficiently small displacements on all of the modes. So this is the 3rd class of GKP, or sorry, 3rd class of bosonic stabilizer codes. Again, a discrete stabilizer group, but this time infinite dimensional logical space. So so with that I'll conclude, and next time we're going to do the 2nd class of codes here. Thank you. maybe I drew it badly, but they're not supposed to over. Oh, the correctable shifts do overlap with the detectable ones. Are you?
Even if you correct it wrongly, how come it's detectable?
Right. So if you consider this shift that takes this point over here, is that what you're saying? That's not correctable. Right. Yeah. These regions are sets of values of all correctable or detectable displacements respectively. So I'm just plotting those values here around the central point, because then in that case they literally correspond to displacement amounts by which you can displace and still be correctable or detectable. In reality, of course, every point is linearly, shifted, and as long as each point stays within its own unit cell, you're good. Okay, and this unit cell is more generally called a Voronoi cell. And this type of geometric interpretation is something that you can always do for all error correcting codes, and classical and quantum. You have some points in a space, they pack the space in some nice, probably uniform way. Each one has a set of points that is closest to it than to any other point. That's called a unit cell in the lattice perspective. It's called a Voronoi cell in general. And error correction happens by mapping an error point into the center of the Voronoi cell that it's in. So as long as the point doesn't leave the Voronoi cell, you're correctable.
With respect to the same slide, so should the detectable shift be everywhere besides like outside of the actual grid point?
Yes. Yes.
Like any shift that does not coincide with exactly the grid is detectable.
Yeah. Exactly. Yeah. So as a but the shifts are labeled by how much you shift. And so, like, if you shift by root pi over 2, that corresponds to this point. Right? These are just these shifts that are correctable or detectable.
Yeah, like taking the module of whatever.
These also describe how this point moves. But I'm not describing how this point moves here. I'm plotting you the region of all the correctable or detectable shifts. Yeah, it's just graphic. Yeah. Yep.
Thank you. So in that index there, there is a maximum maximum value.
Right. Good. So just like before, there was a question about non-normalizability. These again are ideal infinite energy non-normalizable states. They're the same in the same sense as distributions in the first slide that I showed you. So these again don't exist in the lab. So how do you mitigate that? Well, again, you have two infinities to take care of. One infinity is the fact that these are position states. They're infinitely localized states of position. You substitute in sort of Gaussian envelopes of position that are like very, very sharp. Those are called squeeze states, squeezed in position. So then every one of these becomes some state that's squeezed in position for some squeezing amount. Yeah.
More elemental, they are the rules for lower than rating state for another. So really that is a perfect analogy with the spin environment. Because there is a upper value going. So you must have a value state.
You mean you're saying this should have a maximum number? Well, no, I disagree because this is linear momentum, not angular momentum. And even angular momentum can be unbounded.
Because of the rules of composition of the group,
But linear momentum and linear position are both real valued.
that is the rule of lower and raising angular momentum. Linear momentum in quantum mechanics don't follow that rule. So,
The angular momentum isn't present in here at all. There's no angular momentum. It's all linear.
I'm saying that the rectangle, right? The rule of raising and lowering space from the ground is 0
They look like angular momentum because you're superimposing over integer values. Is that what you're saying? Well, I'm happy to chat. Yeah, so just to conclude the thought, the second infinity here is coming from the fact that there's an infinite number of these states. And even though they are themselves normalizable, once we squeeze them, there's an infinite number of them. And so we have to regularize or just put a Gaussian envelope next to this state that depends on L squared. So e to the minus L squared times some parameter delta. And this parameter delta determines the energy of this GKP state. As delta goes to 0, the exponential goes away, and then you're back to this ideal case. So this is just a standard way that they normalize these states. So it looks like this nice comb of decreasing peaks, where each peak is a sharp Gaussian. That's what the state really looks like in the real world. Yeah.
If you're squeezing in the position state,
Yeah.
isn't that a problem for squeezing in the momentum state? Or is it?
Well, if they're highly squeezed, it's not so bad. Right. There will be intrinsic memory errors because you have Gaussian wave packets, and so Gaussians do overlap slightly. So there are intrinsic memory errors for the non-ideal states. Those intrinsic memory errors disappear exponentially with the energy of the state. And so you basically have to tune, if you want to achieve epsilon imprecision at most, you have to tune the energy so that the overlaps only give you epsilon intrinsic memory error.
We are running out of time, but maybe I could ask. So we spent this lecture on GKP, but still we didn't see any of those famous pictures of red and blue arrays.
Well, I'm a theorist. Here's some pictures. This is a square lattice GKP state that's the maximally mixed state on the code space. So what's interesting is that maximally mixed states on GKP states form the code lattice, and there's no negativity. Wigner negativity is the blue part where the Wigner function is negative. I still do not know of a good answer to why there's no negativity here. Negativity is usually a sign of quantumness, for those of you who know. These are pretty damn quantum, but they're not negative. Now, if you look at individual code states, like logical 1 or logical 0 or logical plus, those do form lattices where the dots now become red, blue, red, blue, red, blue. However, the maximally mixed state, which is the projection in the code space, which you can think of as a fingerprint defining the code, is positive. Yeah.
Is that Gaussian weighted, like?
Yeah, see, you see the Gaussian envelope, yeah. This is for a hexagonal lattice. I mean, obviously. And these are the other codes we're going to study next time. This one is binomial code. See the negativity? This is cat. This is a numerically optimized code called square root of 17. See how different these are? Also see how each point here is a non-physical state. You can't have a state localized both in position and momentum at the same time. However, the code space is spanned by superposition, or spanned by like multiple such states. So in the end, the full grid is a valid state, even though each point in the grid is not a valid state. It's completely mind-blowing if you see this for the first time. And this is all due to the fact that the coherences between all these position states interleave and overlap with each other such that you get this nice clean lattice at the end. It's kind of very weird.